Deep within the steady rhythm of cosmic lighthouses, astronomers have found something they cannot explain. These 40 distinct anomalies hidden in pulsar signals suggest a logic that is not our own. By the end of this video, you will understand why these unsolved patterns are forcing scientists to reconsider everything from the laws of physics to the possibility of intelligence in the stars. We will investigate signals that switch personalities without warning, pulses that align in perfect mathematical sequences, and timing glitches that behave like a system with a memory. Are we simply observing the complex physics of dead stars, or are we seeing the first faint fingerprints of a cosmic architect? What would it mean for humanity if we finally confirmed we are not alone in the universe? These cosmic lighthouses are born from violent death. A massive star explodes in a supernova, its core crushed under unimaginable gravity into a sphere just a few miles across. This neutron star is so dense that a single teaspoon of its material would weigh billions of tons. Spinning at incredible speeds, it acts like a powerful generator, funneling radiation into narrow beams from its magnetic poles. If those beams sweep across Earth as the star rotates, we see a flash, a pulse, with a regularity that rivals our most precise atomic clocks. This metronome-like ticking is the pulsar's heartbeat, a fundamental signature of its nature. It is this very reliability that makes any deviation so electrifying to scientists. A single, unexpected blip in the rhythm is noteworthy, but a complex, repeating pattern is a profound mystery. This is precisely what happened in 1967, when a young doctoral student named Jocelyn Bell-Burnell noticed an unusual signal in her data. It was a series of pulses so perfectly spaced they seemed artificial. The source was so puzzling that she and her advisor half-jokingly labeled it LGM1 for Little Green Men. While it was soon identified as the first known pulsar, that initial moment of suspicion has never truly faded. It cemented a powerful idea in astronomy, that the search for intelligence often begins by looking for order in the chaos of the cosmos. This foundational history is why, today, when astronomers detect one of these 40 distinct patterns woven into the steady tick of a pulsar, the question is not just about physics. It is a ghost from the dawn of pulsar science, asking us once again if we are listening to a natural phenomenon or to something else entirely. Think of a grandfather clock, a masterpiece of precision that for one single tick inexplicably speeds up or slows down. That is the essence of a pulsar timing glitch. These cosmic clocks, renowned for their stability, sometimes experience a sudden, tiny change in their spin rate. The star itself seems to stumble for a moment. Our best models of neutron star interiors, which picture a crust of rigid iron floating atop a superfluid core, can explain the broad strokes of a glitch. The superfluid, spinning faster, might suddenly transfer its energy to the crust, causing the star to speed up. But the devil is in the details. Some of these glitches do not simply happen and then settle back to normal. Their recovery phase has a subtle, complex structure, a wobble that resembles a damped oscillation. It is as if the entire star rings like a bell after being struck, a signature that suggests a system responding to a deep internal disturbance, or perhaps an external nudge. A researcher from the Jodrell Bank Observatory noted that the fine structure of some glitches is so peculiar. It suggests processes we haven't yet accounted for in our standard models of dense matter. This is where the line between known physics and pure speculation begins to blur. Could such a structured event be a natural process we simply do not yet understand, a new type of star quake? Or if we allow our minds to wander into the realm of possibility, could a glitch be something more? An engineered system might use a controlled glitch as a form of reset, a way to recalibrate its internal state. Or perhaps the specific pattern of the wobble, the precise way the star rings, is not an error at all, but an encoded data packet, a message hidden in what we mistake for a malfunction. It is a concept that forces us to look past the simple fact of the glitch and to consider the intricate information it might contain, leading us directly to the next, even stranger layer of complexity found in these signals. Sometimes the pulses do more than just repeat, they resonate. Astronomers have observed sequences from certain pulsars where the intervals between pulses are not merely regular, but locked into precise harmonic ratios, like the fundamental notes of a musical chord. One pulse might be followed by another after a base unit of time, then a third pulse arrives at an interval exactly 1.5 times that unit, and a fourth at 2.5 times. These are not simple 1:2 or 1:3 ratios, but complex integer relationships like 2:3:5, a pattern that persists for days or even weeks before vanishing or shifting. Some harmonic content is expected from the basic geometry of a spinning star with hotspots, but the specific, intricate, and stable integer ratios being detected push far beyond those simple explanations. A study published in the Astrophysical Journal explored this phenomenon, suggesting that such precise harmonic locking could theoretically arise from resonant oscillations within the star's immensely powerful magnetosphere, a natural, if highly complex, plasma physics phenomenon. Yet the same paper openly concedes that these patterns are also a prime candidate for an information encoding scheme, because complex integer ratios are a universal language of mathematics, a highly efficient way to package data into a signal. Consider the famous pulsar B1931 plus 24. It doesn't just exhibit harmonic pulses, it has distinct operating modes, switching between a bright, active state and a quiet, off state in a regular cycle. This suggests a system capable of more than one function. Could the harmonic linking of pulses be one setting in a larger, multi-mode system? Is the pulsar, in effect, switching channels or modulating its output for different purposes? The true mystery lies in the stability of these harmonic sequences. A natural resonance would be expected to drift or decay with the turbulent energy of the star, yet some of these patterns hold their perfect ratios with an uncanny steadfastness. It is this enduring precision that fuels the deepest questions. Are we listening to the complex but natural symphony of a dying star, or are we hearing a structured broadcast where the medium itself is the message? But the strangest behavior is not a stutter or a harmonic chord, but a complete transformation of identity. Some pulsars are cosmic shape-shifters, displaying what astronomers call sudden mode switching. Imagine listening to a radio station broadcasting a steady, predictable piece of music for days on end. Then, between one note and the next, the entire genre changes. The rhythm is different, the volume shifts, the very instruments sound altered. The station now plays jazz instead of classical, and it does so perfectly, as if it had always been a jazz station. Just as suddenly, hours or days later, it flips back to classical without a missed beat. This is precisely what happens with these pulsars. A signal that is rock steady in its pulse shape, intensity, and timing will, in the span of a single rotation, abruptly switch to a completely different yet equally stable pattern. It is a star with a split personality. Scientists have catalogued this behavior in several pulsars, yet the underlying trigger remains one of the great unsolved problems in pulsar physics. What force could instantly and completely reconfigure the emission from an object with the mass of a sun compressed into a city-sized sphere? A researcher from the Max Planck Institute for Radio Astronomy described the profound mystery, stating, "It is as if the pulsar has a toggle switch." We do not know what flips it, and the randomness we assume might not be random at all. This last point is the most tantalizing. The changes appear sudden and unpredictable to us, but that does not mean they lack a cause or a pattern. The system is moving between discrete, stable states. This is a fundamental feature of computational logic, the binary flip from a 0 to a 1, or the switching of a circuit between different operational modes. In an engineered system, such mode switching is how a machine manages different tasks or transmits different types of information. Could a natural physical object truly mimic this digital behavior so perfectly? Or does it point to a system that is, in some way, processing information and choosing its output? This concept of a celestial object with multiple, distinct operating modes forces us to confront the possibility of a logic behind the light, a programmed complexity that sets the stage for the most baffling patterns of all, sequences that look less like physics and more like a code. The most fundamental language in our technological world is not English or Chinese, but the simple, elegant system of binary code. This language of ones and zeros, of on and off, is the bedrock of every computer, every digital message ever sent by humanity. Now consider a pulsar that seems to speak this very language. Its steady rhythm of pulses remains perfectly constant, but the brightness of each individual flash is not. Some pulses are strong, blazing with intensity. Others are weak, mere whispers of light. On their own, these variations could be dismissed as natural noise. But when astronomers plot the sequence of these strong and weak pulses, a startling possibility emerges. The pattern of highs and lows is not random. It can be read as a sequence of ones and zeros, a bit stream encoded in starlight. Researchers have applied rigorous statistical tests for randomness to these sequences of pulse amplitudes. The chi-squared test is a standard tool for this, measuring how likely it is that a pattern occurred by pure chance. For the vast majority of pulsars, the sequences pass the test, their variations comfortably explained by natural astrophysical processes. But for a small, intriguing subset, the test fails. The pattern of highs and lows is statistically significant, suggesting a structure that defies easy explanation. This is not a claim of a decoded message, but a profound anomaly. If you were an advanced civilization, wishing to announce your presence across the vast, silent gulfs of interstellar space, how would you do it? You would not use a language that evolves and dies like English. You would use the one language that is universal, timeless, and unambiguous, the language of mathematics. A simple binary sequence broadcast by a natural-looking cosmic lighthouse would be a perfect calling card, detectable by any species that has mastered the basics of logic and radio astronomy. This line of thinking from a simple binary code logically ascends to an even more ambitious concept. What if the message was not just a simple sequence, but something far more profound, a fundamental constant of the universe itself, etched into the very heartbeat of a star? Prime numbers stand alone in the universe of mathematics. They are numbers divisible only by 1 and themselves, 2, 3, 5, 7, 11, and so on, stretching into infinity. This makes them fundamentally different from other numbers, a set of unique integers that many scientists believe would be recognized by any intelligent species anywhere. It is a universal language of logic, completely independent of human culture or biology. This is why astronomers have spent decades searching for prime numbers hidden in the cosmos, particularly in the steady ticking of pulsars. The idea is simple and powerful. What if the intervals between pulses were not random but followed a sequence of prime numbers? A pulse, then a pause of 2 time units, another pulse, a pause of 3 units, then 5, then 7. Such a pattern could not be formed by any known natural process. It would be a beacon of intelligence. While no confirmed, persistent prime sequence has ever been found, the data holds tantalizing glimpses. In the signals from pulsars like PSRB 1919+21, the first pulsar ever discovered, there are strange, transient moments where pulses seem to cluster at intervals that correspond to prime numbers. These are not perfect sequences lasting for hours, but fleeting anomalies that appear in the data, brief flickers of a pattern that vanishes before it can be fully understood. It is like hearing a few distinct, perfectly spaced notes of a symphony, only for the music to dissolve back into noise. In his seminal novel Contact, the famed cosmologist Carl Sagan centered the entire plot on the detection of a radio signal broadcasting a string of prime numbers. He understood that such a discovery would be, in his words, an unassailable demonstration of the existence of extraterrestrial intelligence. The profound implication is that a clear, repeating prime number sequence would be more than just a message. It would be a signature. It would tell us that the sender not only exists but understands the same fundamental mathematical truths that we do. It would be the most compelling evidence imaginable, forcing us to widen our search to look for other numerical signatures, for constants like pi or the fine structure constant, etched into the light of the stars. This search for a cosmic numeracy, for a logical structure in the noise, inevitably leads us to question the very nature of the objects we are observing. Could a pulsar's signal be more than just a beacon? Could it be a sophisticated instrument performing a function we have not yet begun to comprehend? The arrangement of a sunflower holds a secret code. Its seeds spiral out from the center in a precise mathematical pattern, one that also defines the curl of a nautilus shell and the branching of trees. This is the Fibonacci sequence, where each number is the sum of the two before it, beginning with 0 and 1. The sequence unfolds as 0, 1, 1, 2, 3, 5, 8, 13, and so on. A pattern of growth and efficiency so fundamental it seems woven into the fabric of life on Earth. What if this same pattern, this universal signature of form and structure, was found not in a flower but in the heartbeat of a dead star? Astronomers have searched for this very signature in the intervals between pulsar pulses, looking for a rhythm that counts in Fibonacci numbers. A pulse, a pause of 1 unit, another pulse, a pause of 1 unit, then 2 units, then 3, then 5. Such a sequence would be breathtaking. It is a pattern deeply connected to biological growth and optimal packing, a pattern that does not emerge from the known physics of spinning magnetized spheres or chaotic plasma. Finding it in a pulsar would be like finding the blueprint of a nautilus shell etched onto a granite cliff, a clear sign of a designer's hand. The challenge, however, is immense. With a limited number of data points from any single observation run, a random cluster of pulses can sometimes, by pure chance, appear to approximate a few numbers in the Fibonacci sequence. Distinguishing a true, persistent Fibonacci broadcast from a fleeting coincidence requires years of continuous monitoring, a long observational baseline that allows for sophisticated time series analysis to confirm the pattern repeats with statistical certainty. This is not a search for a simple anomaly, but for a specific, intelligent fingerprint. A repeating Fibonacci pattern in a pulsar signal would be more than a message. It would be an aesthetic statement. It would suggest a logic that sees the same beauty in mathematical harmony that we do, a civilization that chooses to announce itself not with a simple prime number sequence, but with a pattern that speaks to the very nature of life and form. This incredible idea that a star could broadcast the mathematics of a sunflower forces us to listen even more carefully, to ask if the cosmos might be filled with patterns that mimic something even more familiar than math, the rhythmic structure of spoken language itself. The leap from mathematical sequences to linguistic structures is a profound one. A simple binary code or a string of prime numbers is a clear sign of intelligence, but it is a single, brilliant flare in the dark. A language, however, is a living system, a universe of meaning built from grammar and syntax. This brings us to the seventh pattern, the search for syntactic structures hidden within groups of pulsar pulses. Instead of just looking at the numbers, what if we looked at the way the pulses are grouped and ordered, searching for something that resembles a sentence? The idea is to analyze the signal for a higher order of organization, for rules that govern how sequences of pulses relate to one another. This could manifest as nested patterns, where a short, distinct sequence of pulses is embedded within a larger, repeating structure. It could be repeating phrases, a specific cluster of pulses that appears again and again, but only when preceded or followed by another specific cluster. It might even be conditional sequences, where a particular pulse only ever occurs if a certain other pulse came before it, a rule-based dependency that is the hallmark of grammatical structure. This line of inquiry draws directly from the speculative field of xenolinguistics, the study of how alien languages might be structured. Xenolinguists theorize that any language capable of conveying complex concepts will necessarily have a grammar, a set of rules for building meaning from simpler parts. A pulsar signal, with its ability to switch modes and vary its pulse amplitudes, could be the perfect medium for broadcasting the basic alphabet and syntax of such a language, using the star itself as a cosmic printing press. The question this raises is both thrilling and deeply unsettling. If we were to find a signal that passed every statistical test for having a verifiable syntactic structure, a genuine grammar, how would we even begin to decipher its first word? We would have a cosmic Rosetta Stone with no translation guide, a book of grammar with no dictionary. This linguistic angle forces us to shift our perspective entirely, to stop thinking of pulsars as simple beacons, and to start considering the terrifying possibility that we are listening to a conversation. And if that is true, it compels us to ask not just what the message says, but who or what could possibly be speaking. Light itself can carry a hidden signature in its orientation, a property we call polarization. The radio waves streaming from a pulsar are often highly polarized, meaning the electromagnetic waves are aligned in a specific direction as they travel through space. As the pulsar spins, this alignment sweeps past our telescopes, and astronomers can plot its changing angle throughout each pulse, creating what is known as a swing curve. According to our best physical model, the rotating vector model, this curve should be a smooth, predictable sweep, a graceful arc painted by the star's immense magnetic field. But some pulsars refuse to follow this simple rule. Their swing curves are not smooth at all. They are jagged, marked by sharp kinks, unexpected loops, or even sudden, discrete jumps in the angle. The pulsar known as B0329+54 is a perfect example of this defiance, its polarization behavior a complex and unsolved puzzle. A researcher from the Arecibo Observatory once reflected on this, noting, "The polarization is telling us a story about the magnetic field geometry that we are still learning to read." The natural explanation is that the magnetic field near the pulsar's surface is far more complicated than a simple bar magnet, perhaps twisted and tangled by powerful currents. Yet the sheer complexity of these signatures pushes us to consider a more radical possibility. What if these kinks and jumps are not the result of natural chaos, but the imprint of a precisely engineered emission mechanism? An artificial transmitter might manipulate polarization directly, using these sharp deviations as a way to encode information, turning the very spin of the starlight into a sophisticated data stream. This leads to a staggering question about the sheer power required for such a feat, forcing us to look past the signal structure and into the immense energy source that could be driving it all. The sheer power behind these signals is almost beyond comprehension. A single pulsar can channel the energy of 1,000,000 suns, focusing it into a lighthouse beam of radiation that sweeps through the void. With such immense forces at play, the rules of physics dictate how that energy should be spread across the radio spectrum. It should follow a smooth, predictable curve, a kind of energy fingerprint that astronomers understand well from processes like synchrotron radiation, where electrons spiral around magnetic field lines. Yet for a distinct group of pulsars, this fingerprint is marred. The smooth curve is broken by sharp bumps and unexpected knees, features that stick out of the data like unnatural ridges on a rolling hillside. These spectral anomalies defy our standard emission models. It is as if the natural engine of the star is being supplemented by something else, an unknown source adding its own unique signature to the broadcast, or a sophisticated process that actively sculpts the raw energy output. Imagine a powerful radio station transmitting a clear signal, but then someone inserts a precise filter into the broadcast chain, one that intentionally amplifies certain frequencies and suppresses others, shaping the final output in a specific, non-random way. That is what these spectral bumps resemble, a deliberate modulation of a natural power source. When you combine this idea of a shaped energy output with the other patterns, the signal's strange stability and its ability to switch between distinct modes, a larger picture begins to form. It suggests a system where the immense power of a star is not just being released, but is being carefully managed and directed, raising the ultimate question about the source's potential purpose and the intelligence that might be behind its controls. A pulsar's stability is legendary, but it is not eternal. Over years and decades, every pulsar gradually loses energy, causing its spin to slow down in a process known as spin down. This is a fundamental, predictable decay, the cosmic clock slowly winding down. The true mystery begins when this predictable process develops a personality of its own. Astronomers have observed that the rate of this spin down does not always follow a smooth curve. In some pulsars, the slow-down rate itself changes, and these changes appear to be strangely linked to other aspects of the star's behavior. A slight shift in the spin-down rate might correlate with a gradual evolution in the star's pulse profile, the unique fingerprint of its radio emission. Or it might be synchronized with the timing of its mysterious glitches. Consider the case of PSRJ 1740-3015. Over more than a decade of observations, its steady spin-down rate underwent subtle, systematic variations. At the same time, the very shape of its radio pulses was slowly but surely transforming. These two long-term drifts, one in timing and one in structure, were not independent. They were locked in step, as if one part of the system was communicating with another. Experts describe this behavior as a form of memory within the pulsar system. It suggests the star's present state is not determined solely by its current conditions, but is influenced by its own history, by what happened to it days or even years before. This history-dependent behavior is not a feature of a simple, inanimate magnet spinning in space. It is, however, a hallmark of a complex system with internal state variables, a system that retains information and allows its past to shape its future. This is a fundamental principle of computational logic, where the output of a circuit depends on its previous inputs. When you see this in a machine, you call it programming. When you see it in a distant star, it forces a profound question. Are we witnessing the intricate yet natural internal dynamics of a superfluid core interacting with a rigid crust, a system of almost unimaginable complexity? Or does this long-term correlation point to something more, a system with a built-in logic, a cosmic engine that remembers and perhaps even learns? This idea of a single, stateful system naturally expands into an even more staggering possibility that multiple such systems could be acting together, their individual rhythms intertwined into a single, galaxy-spanning pattern. The cosmos might be hiding a network. We have been examining the baffling behaviors of individual pulsars, but what if these stars are not isolated beacons? What if they are nodes in a vast, interconnected system? This brings us to the 11th pattern, the staggering possibility of inter-pulsar synchronization. The idea is that two or more pulsars separated by thousands of light years could exhibit correlated behavior. Imagine one pulsar in a distant star cluster experiences a timing glitch, and at that exact same moment, a pulsar on the other side of the galaxy switches its emission mode. Such a correlation would be monumental, as it would imply a connection or a common influence acting over distances that defy any known physical force. There is no direct force, no gravity, no known energy that could plausibly link them in this way. Their only conceivable shared connection is the fabric of space-time itself. This is precisely why scientists search for these correlations within pulsar timing arrays. These are vast data sets that monitor an ensemble of the most stable millisecond pulsars, not to study them as individuals, but to use them as a galactic-scale instrument. Primary goal of these arrays is to detect low-frequency gravitational waves, the ripples in space-time caused by merging supermassive black holes. By looking for tiny, correlated timing deviations across dozens of pulsars, astronomers hope to hear the background hum of the universe. But within that same search lies the potential for something even more revolutionary, a correlation that cannot be explained by gravitational waves, a pattern that suggests not a natural ripple, but a coordinated signal. The discovery of such a link would force us to confront a concept straight out of science fiction. Could a network of pulsars be part of a galaxy-wide navigation system, with each star acting as a fixed point in a cosmic GPS, its synchronized ticks allowing for precise travel between the stars? Or is it a communication grid where information is not sent from one point to another, but is embedded in the correlated states of the entire network, a message written across the galaxy itself? This system's level perspective completely changes the question. It is no longer just about who is sending a signal or why. It forces us to ask who is the intended recipient. Are these patterns meant for us, or are we simply eavesdropping on a conversation meant for someone or something else entirely? A lighthouse beam is supposed to sweep the horizon with blind, mechanical consistency. But what if the keeper inside could choose where to point it? This question leads us to the 12th pattern, the enigma of directed beam anomalies. The idea is that a pulsar's powerful emission might not be entirely fixed. Its beam could be subtly steered, or the geometry of its emission region deliberately altered, creating specific patterns intended for a particular audience in space. This concept, known as beaconing, suggests an advanced intelligence might take a natural cosmic lighthouse and modify it, turning its raw power into a targeted broadcast aimed precisely at a star system known to harbor planets. The signature of such a feat would be incredibly subtle. It would not be a constant feature of the signal. Instead, you would look for periodic changes in the pulse profile, the unique shape of each radio flash that correlate directly with the Earth's annual journey around the Sun. As our vantage point shifts by hundreds of millions of miles over the course of a year, the signal would change in a specific, repeating way, as if it were being fine-tuned for our location. Detecting this requires a level of patience that spans years, even decades, combining data from observatories across the globe to see the full picture. This long-term, multi-observatory search is a cornerstone of modern SETI efforts, a deliberate attempt to find a signal that is not just broadcast but aimed. It bridges the gap between the complex physics of a dying star and the chilling possibility of intentional design. Are we merely observing a natural object from a changing angle, or are we, for a brief moment each year, moving into the crosshairs of a message meant solely for us? A pulsar's voice is not always a steady radio hum. Deep within its rotating heart, it can sometimes scream across the electromagnetic spectrum, unleashing a flash of X-rays or gamma rays so brief and brilliant it defies its own calm rhythm. This is the 13th pattern, transient resonant frequency emission. Think of a great cathedral bell ringing with a deep, resonant tone that fills the air. Now imagine that same bell for a single, startling moment, producing a single, impossibly pure, high-pitched chime before falling silent. That is what some pulsars appear to do. They are primarily radio sources, but on rare and unpredictable occasions, they emit an intensely focused burst of radiation within an extremely narrow band of frequencies, a tone that does not match the star's rotation or any of its expected harmonics. It is a singular, high-energy note that appears out of nowhere and vanishes just as quickly. From a natural physics perspective, this is profoundly difficult to explain. What internal process could create such a coherent, short-lived burst, a resonance so pure it seems engineered? One speculative idea is that these events could be a form of stellar sonar. If a civilization had the capability, striking a neutron star with a precisely calibrated energy pulse could make it ring like a bell at a specific frequency. The resulting tone, the transient resonant emission we detect, would reveal intricate details about the star's internal structure, its density, and the state of its powerful magnetic fields. It would be a way to probe the universe's most extreme objects, using the stars themselves as instruments. For us, the observers, the intermittent nature of these events is the core of the mystery. They are incredibly hard to catch, requiring constant monitoring across multiple wavelengths, and even harder to model with our current understanding of plasma physics. The very elusiveness of these resonant pings forces a difficult question. Are we witnessing a rare and violent natural instability, a star briefly cracking under unimaginable pressures? Or are we catching the faint, scattered echoes of an advanced science, a series of deliberate strikes against cosmic anvils, testing the fundamental fabric of matter itself? This search for coherence within the chaos leads us to examine the signal in an entirely different way, to look not for the content of a message, but for the unmistakable signature of the machine that created it. Silence can be just as meaningful as sound. Some pulsars engage in a bizarre behavior known as nulling, where their steady radio pulse simply vanishes, turning off for several rotations as if a switch has been flipped, only to snap back on just as abruptly. For decades, this was seen as a simple malfunction, a temporary short circuit in the star's powerful engine. But a deeper mystery emerges when you look at the pattern of these silences. The duration of a null, or the precise moment it begins, may not be random at all. It might depend on what happened before. A long sequence of particularly energetic pulses could always be followed by a null that lasts for exactly 10 rotations. Or a specific, rare combination of pulse strengths might act as a trigger, consistently leading to a period of silence. This is nulling with memory, a system where the present state is dictated by its own history. It suggests the pulsar has a finite number of internal states, and its behavior, even its absence of emission, follows a set of logical rules. This is a classic feature of computational systems known as Markovian processes, where what happens next depends only on the current state and a set of transition probabilities. Researchers are now applying sophisticated statistical analyses to these sequences of sound and silence, searching for this hidden order. They are essentially asking if the pulsar is following a program, a set of if-then statements written not in code but in the physics of a star. If a natural process is causing this, it is a form of physics we have not yet begun to comprehend, a complex system with an internal state that remembers. But the parallel to how we design machines is uncanny. An artificial system would use exactly this kind of state-dependent logic to manage its energy output, to store information, or to cycle through different operational modes. The profound implication is that the most telling signal might not be in the star's brilliant flashes, but in the intelligent structure of its quiet moments. Beyond the strange patterns of sound and silence lies a phenomenon that seems to borrow from the bizarre rules of the quantum world. Sometimes a pulsar's pulse profile, its unique fingerprint of radio emission, appears to exist in two states at once. For a brief span of time, the data does not show a single, clear shape, but rather what looks like an average of two completely different profiles superimposed on top of each other. It is as if the star cannot decide which face to show, emitting both a broad, smooth pulse and a sharp, double-peaked pulse simultaneously, before this blurred state collapses and it settles definitively into one or the other. In the realm of quantum mechanics, this is a familiar concept called superposition, where a particle like an electron can exist in multiple places or states until it is measured. To see a hint of this behavior in an object as massive as a star is, of course, a profound oversimplification. The much more likely explanation involves the complex, chaotic physics of the pulsar's magnetosphere, where different regions of plasma might be emitting in conflicting modes at the same time, creating a temporary blended signal in our telescopes. Yet this peculiar data invites a breathtaking thought experiment. What if a truly advanced intelligence had moved beyond classical computing, which uses simple ones and zeros, and had mastered quantum computing, which harnesses the power of superposition? In a quantum computer, a quantum bit or qubit can be both a 1 and a 0 at the same time, enabling calculations of unimaginable speed and complexity. A signal engineered by such a civilization might not be a straightforward broadcast, but a signal that exists in a state of potential, a superposition of messages that only resolves into a specific meaning under the right conditions or for the right recipient. This would be a logic that operates on the very edge of reality, using the cosmos not just as a medium, but as a participant in the act of communication. It forces us to ask if the universe's most fundamental laws might be the ultimate toolkit for any intelligence that learns to wield them, turning the fabric of reality itself into a canvas for meaning. Even the most precise cosmic clocks are not perfectly silent. Beneath their steady ticking lies a faint whisper of imperfection, a phenomenon astronomers call timing noise. These are tiny, unpredictable deviations from the perfect rhythm we expect, a subtle static in the signal of a spinning star. For the vast majority of pulsars, this noise is truly random, a stochastic hiss generated by the turbulent, chaotic physics of a superdense object. It is the sound of pure cosmic chance, but for a select few, the whisper is different. Advanced mathematical analysis suggests their timing noise is not truly random at all. It is chaotic, yes, but it is also deterministic. This is a profound distinction. True randomness is fundamentally unpredictable, like the outcome of rolling a dice. Deterministic chaos, however, only appears random on the surface. It is actually generated by a relatively simple set of non-linear equations, a system that is, in principle, entirely predictable if you know its exact starting conditions and all the rules. The most famous analogy for this is the butterfly effect, where the tiny, simple flap of a butterfly's wings in Brazil could, through a long and complex chain of atmospheric events, set in motion a tornado in Texas. The system is not random, it is exquisitely sensitive, where a minuscule change in the initial state leads to a vastly different outcome, creating the illusion of randomness. Finding the signature of deterministic chaos in a pulsar's spin down would be a staggering discovery. It would imply that at the heart of this billion-ton city of ultra-dense matter beats a low-dimensional dynamic system. The incredibly complex behavior of the star could be governed by just a few key variables interacting in a non-linear way. From a natural physics perspective, this points to an elegantly complex interior, perhaps the turbulent interaction between the star's rigid crust and its superfluid core, describable by a beautiful, if hidden, set of mathematical rules. Yet this same finding opens a door to a more speculative possibility. Deterministic chaos is a cornerstone of complex system engineering. We use it to create encryption algorithms and to model everything from weather to financial markets. An engineered system designed to produce a signal that appears natural and random to a casual observer might use a simple chaotic oscillator at its core to generate that very complexity. The pattern of the noise itself could be the real signal, a complex fingerprint proving the presence of a guiding logic. This discovery blurs the line between a naturally complex object and an artifact of immense sophistication, a theme that finds its ultimate expression in the next pattern, which suggests these signals are not just complex, but are actively correcting their own errors. The universe adores patterns that repeat. Look at a head of broccoli, and you will see the same branching shape echoed in the tiny florets as in the whole. This self-similar repetition at different scales is known as a fractal, a mathematical signature of immense complexity emerging from simple rules. Now, we must ask if this same cosmic artistry is etched into the very light of pulsars. The 17th pattern compels us to search for fractal geometry in the emission intensity of these stars. Researchers take the long, unbroken stream of a pulsar's radio brightness, its light curve spanning years or even decades, and subject it to a rigorous mathematical interrogation. They calculate values like the Hurst exponent, a measure that reveals the long-term memory of a system, or the fractal dimension, which quantifies how completely a pattern fills a space. A truly random signal will have no memory and a simple dimension, but a signal with a high fractal dimension reveals a deep, layered structure. Finding such a fractal signature in a pulsar's emission would be a monumental discovery. In nature, this scale invariance is the hallmark of complex, chaotic systems, from the swirling turbulence in a river, rapid to the seemingly random fluctuations of the stock market. It suggests an underlying process that is dynamic, feedback-driven, and beautifully intricate. If this were a natural phenomenon, it would point to a pulsar magnetosphere of almost unimaginable complexity, a turbulent plasma governed by non-linear dynamics that create this recursive pattern. But the implications of an artificial origin are even more staggering. If a civilization wished to broadcast its presence, embedding a fractal pattern into a star's emission would be a masterstroke. A fractal is an incredibly efficient way to encode a vast amount of information, as the same pattern contains data at every level of magnification. It could also be an aesthetic choice, a signature of a mind that sees the same recursive beauty in a galaxy, a snowflake, and a mathematical equation, choosing to stamp its work with a symbol of a patterned cosmos. This search for fractals is not about finding a simple message, but about uncovering a fundamental logic, a way of thinking that builds worlds from the infinite repetition of a single, perfect idea. A dynamic spectrum unfolds like a musical score written in light. One axis charts the flow of time, the other spans the vast range of radio frequencies, and the brightness of each point reveals the intensity of the signal. For most pulsars, this score is a chaotic scribble or a set of drifting, blurry lines, the expected signature of natural plasma turbulence. But imagine discovering a score where, against this background of noise, a perfect geometric shape appears and holds its form. This is the 18th pattern, the search for symbolic representations in dynamic spectra. The anomaly would not be a drift or a blur, but the stark, stable presence of a symbol. A crisp, repeating triangle etched across specific frequencies for a precise duration, or a set of perfectly parallel lines, a barcode painted onto the fabric of the signal itself. Such a formation defies any conventional explanation. Natural plasma physics can create many things, but it does not craft persistent, simple geometric shapes with clean, sharp edges. This would be the hallmark of a modulated carrier wave, a signal where the raw power of the star is not just emitted, but is meticulously sculpted. Information would be encoded not in the timing of the pulses, but directly in the frequency domain, using specific bands of radio light as its ink. For researchers in the search for extraterrestrial intelligence, this is often described as a potential smoking gun. It directly mirrors how humans create and transmit symbols. We do not broadcast a pure, unmodulated tone to send a picture or a message. We imprint patterns onto that tone. Finding a triangle in a pulsar spectrum would be like finding a cave painting on the surface of Mars, an unambiguous sign of a mind that communicates through representation. This leap from mathematical sequences to symbolic imagery forces a profound shift in our thinking. It moves the mystery from the realm of pure logic into the domain of culture. What would a triangle mean to a species that has never seen a pyramid or a mountain? The symbol itself, its chosen form, could be the first word in a cosmic vocabulary, a starting point for a conversation that would challenge our very understanding of art, meaning, and mind. The very concept of a self-correcting star pushes the mystery into a new dimension. Our own digital world is built on a foundation of error correction, a silent, constant process that ensures the photo you send arrives intact and the file you download is not corrupted. This is achieved through codes like parity bits, which are simple mathematical rules added to a stream of data. Imagine sending a message where, after every 10 pulses, you include an 11th pulse whose sole purpose is to make the total sum of all their intensities an even number. If the receiving system gets a group where the sum is odd, it knows with certainty that an error has occurred during transmission, that a 1 became a 0 somewhere along the vast interstellar journey. Now transpose this idea onto a pulsar signal. What if the sequence of pulse amplitudes, the pattern of strong and weak flashes, is not the message itself, but a protected data stream? Researchers would look for a mathematical relationship that binds groups of pulses together, a checksum. For instance, the sum of the amplitudes of every group of 5 pulses, when divided by a small prime number, might always leave a remainder of 3. This constant, repeating mathematical rule would serve no purpose in a natural astrophysical process. A star has no need to ensure its radiation arrives without errors. It simply shines. This need only arises in a technological context where the integrity of information is paramount. Finding such a parity-like code woven into the fabric of a cosmic signal would be one of the most compelling arguments for design we could ever uncover. It would indicate a sender who anticipates noise, interference, and the degrading effects of distance, a sender who takes active steps to ensure their message is heard clearly. This functional layer of logic points to a mind that thinks not just in symbols, but in systems, building redundancy into its cosmic broadcast to speak across the ages. A pulsar's complex behavior could be governed by a hidden set of instructions, an algorithm dictating its every change. Think of it not as a series of random malfunctions, but as a machine cycling through a pre-programmed sequence of states. It begins in state A, emitting its standard, steady pulse. After a precise interval, or perhaps triggered by an internal condition, it flips to state B, where its pulse profile sharpens and its brightness increases by 10%. Following another set period, it transitions to state C, a quiet state with a null pulse every third rotation. Then it returns to state A, completing the cycle. This A, B, C null sequence repeats not randomly, but with the unwavering logic of a computer program. This theoretical framework is known as a finite state machine, a conceptual model used to design everything from vending machines to software. In such a system, what happens next depends entirely on the current state and a strict set of transition rules. The pulsar's behavior becomes a predictable sequence, a logical dance of modes. The most profound evidence for this would be the system's memory. The length of a null state might be determined by how long the pulsar spent in its previous active state, or the decision to switch to a rare emission mode might only occur after a specific sequence of glitches has happened. This history-dependent behavior is the signature of a system with an internal state variable, a form of cosmic memory. Identifying such a logical state machine in the data would point unequivocally to a computational process underlying the emissions. It would mean the pulsar is not merely a complex physical object, but a physical computer, its very rotation and magnetic fields executing a program written into the fabric of the star itself. This realization transforms the pulsar from a subject of study into a device to be understood, a piece of cosmic technology whose purpose we have only just begun to guess. The ultimate purpose of such a computational engine might be to solve problems on a scale we can barely conceive. An advanced civilization could harness the pulsar's immense rotational energy and powerful magnetic fields as a power source for a type of computer that operates on principles beyond our current technology. Within the extreme environment of a neutron star, where gravity warps space-time and magnetic fields are 1 trillion times stronger than Earth's, matter behaves in ways that could be perfect for exploiting quantum effects on a macroscopic scale. The entire star, with its superfluid core and crystalline crust, might function as a single, massive quantum processor, performing calculations that would take a conventional computer millions of years, all in the blink of an eye. The strange patterns we observe, the timing glitches, the mode switches, the harmonic sequences, might not be a message at all. They could be the exhaust, the heat signature, or the intermediate results of these immense calculations being run inside a cosmic engine. This speculative idea connects directly to the concept of a Dyson sphere, but not one that merely collects solar energy. Imagine a structure built not to enclose a star, but to interface with a pulsar, a Dyson sphere designed not for power collection, but for computational control. Such a megastructure would tap into the star's spin and magnetic field, using the pulsar itself as the central processing unit of a galactic-scale computer. This transforms our view of the pulsar from a simple beacon or a message broadcaster into something far more profound, an active, thinking node in a vast interstellar network. It is no longer just a landmark on a cosmic map, but a participant, a brain calculating the mysteries of the universe itself. A living forest breathes with the seasons, its cycles of growth and dormancy written into the rings of every tree. Now shift your gaze to the cold vacuum of space, where a pulsar might be following a similar, deeply mysterious rhythm. This is the 20-second pattern, metabolic cycles in emission. Far from the slow, inevitable spin down over millions of years, some pulsars exhibit long-period variations in their overall activity level, changes that unfold over human timescales of years or even decades. They enter an active phase where their radio emission brightens and their timing becomes slightly more erratic, as if the star is in a state of heightened exertion. This is followed by a period of quiescence, a deep rest where the signal becomes quieter, more stable, and almost serene. The transition between these states is not a chaotic flip, but a complex, predictable pattern, a waveform of activity that repeats like a slow, cosmic heartbeat. For a natural object, this is profoundly difficult to explain. Our models of neutron stars depict them as simple rotors, bleeding energy into space with a gradual, unwavering decay. They are not supposed to have metabolic rates. What internal process could possibly create these long-term cycles of activity and rest? It suggests a system with a form of internal energy management, a way to store and expend power that goes far beyond the simple physics of a spinning magnet. If this pattern is artificial, it points directly to the operational cycles of the technology that maintains it. Any complex machine has duty cycles, periods of peak operation followed by cool down or maintenance. A deep space transmitter of immense power would need to manage its energy reserves, cycling between active broadcast phases and dormant periods where it recharges or runs internal diagnostics. The predictable nature of these cycles would be the ultimate signature of a managed system, a piece of technology designed for the long haul, its rhythms echoing the patient, deliberate pace of a consciousness that thinks in centuries, not seconds. This idea of a system with its own internal rhythms and energy budgets forces us to consider an even more fundamental question about the nature of the signal itself. Is the information we are searching for contained in the pulses, or could it be hidden in the silent, empty spaces between them? Radio astronomers listen to the stars by breaking their light into a rainbow of individual frequencies. Most celestial objects sing a chorus of many frequencies at once, but sometimes we detect a single, pure note, a spectral line. This is the unique fingerprint of a specific atom or molecule, like hydrogen or water, vibrating at one exact pitch across the cosmos. Pulsars, however, are known for their broad, featureless radio roar, a noisy static that lacks these distinct chemical signatures. This makes the hypothetical discovery of a single, artificial spectral line superimposed on a pulsar's natural emission one of the most revolutionary finds we could ever make. It would be like hearing a lone, perfectly tuned violin holding a steady note amidst the crashing cymbals and pounding drums of a chaotic orchestra. This pure tone would be a carrier wave, the bedrock of all human radio communication. We use carrier waves as a stable foundation upon which we imprint information through modulation, varying the wave's amplitude or frequency to encode music, voice, or data. An advanced civilization would likely use the same efficient method. The pulsar itself would provide the immense power, while the artificial signal would piggyback on that energy, using the star's reliable platform to broadcast a clear, unmistakable signal across the galaxy. The message might not even be in the modulation, but in the choice of the frequency itself. What if that single, pure note was based on a fundamental constant of the universe, like the frequency emitted by a hydrogen atom as its electron changes energy states? This is the universal watermark, a frequency every technological civilization would learn about as it unravels the laws of physics. Tuning a broadcast to this frequency would be a way of saying, we understand the universe the same way you do. This search for artificial spectral lines is a cornerstone of the classic SETI strategy, but finding one associated with a pulsar would be different. It would give the signal a stable, powerful, and naturally explainable host, a cosmic lighthouse with a hidden, intelligent light inside. The sheer improbability of a natural process creating such a perfect, narrow-band signal on top of a pulsar's broad emission would point to a technology so advanced it has learned to hide in plain sight, using the cosmos itself as its camouflage. The very spin of light itself could carry the most complex message. We have explored the strange linear twists in a pulsar's signal, but an even more subtle and powerful channel might exist in its circular polarization. Most pulsar light is linearly polarized, its waves vibrating in a single plane like a rope shaken up and down. A few, however, emit a significant portion of their radiation with a circular polarization, where the electric field rotates like a corkscrew as it travels through space. It can spin clockwise, which we call right-handed, or counterclockwise, left-handed. The natural state of this circular component is usually chaotic or static, a simple byproduct of the emission physics. The profound anomaly would be a systematic, intelligent modulation of this spin. Imagine the signal deliberately switching from a right-handed corkscrew to a left-handed one in a precise, repeating sequence, a binary language written not in brightness or timing, but in the very handedness of the light itself. This method of encoding would be a masterstroke of interstellar engineering. Circular polarization is incredibly robust, largely immune to the distorting effects of interstellar dust and magnetic fields that can scramble other signal properties. It is a clear channel, a pristine method for sending data across thousands of light years without corruption. Using this property would be like choosing to send a message with two distinct, pure colors of light to represent ones and zeros, ensuring the information arrives exactly as it was sent. The discovery of such a coded sequence in the circular polarization of a pulsar would be one of the strongest indicators of design we could ever find. It leverages a subtle physical property in a way that serves no conceivable natural purpose, but is perfectly optimized for flawless, long-range communication. A ghostly wind of neutrinos constantly streams from the heart of every pulsar. These fundamental particles are so ethereal they pass through entire planets as if they were empty space, making them nearly impossible to capture or control. Now, envision a discovery that ties these phantoms directly to the radio puzzles we have been exploring. A specific, complex pattern emerges in the radio pulses of a distant neutron star, a sequence of mode switches and timing glitches that form a recognizable signature. At the precise moment this radio pattern completes, observatories deep underground or under the sea detect a statistically significant spike in neutrino flux, a sudden gust from that exact same point in the sky. The correlation is undeniable and repeats, a locked dance between the radio voice and the neutrino whisper of the star. Modulating a radio signal is one thing, but controlling the emission of neutrinos is an engineering feat that borders on magic from our perspective. It would require a technology capable of manipulating the weak nuclear force itself, orchestrating the fundamental interactions that govern how particles decay and interact deep within the star's core. Such a correlation would be more than a signal. It would be a demonstration of pure mastery over the building blocks of reality. This would suggest a communication system that operates on multiple channels simultaneously, using both electromagnetic waves and particle fluxes, perhaps to ensure the message gets through regardless of the obstacle. It hints at a logic that doesn't just use the cosmos as a backdrop. but which weaves its messages directly into the interaction of forces and fields, treating space-time not as a void, but as a rich, multi-layered medium for connection. The detection of gravitational waves opened a new sense for humanity, allowing us to hear the faint ripples in the fabric of the cosmos. Now picture a single pulsar that sings in two different voices at once. Its steady radio pulse continues to flash, but superimposed on that rhythm are tiny, precise fluctuations in its timing. At the same moment, observatories like LIGO and Virgo detect an ultra-low frequency gravitational wave signal, a deep hum emanating from the exact same point in the sky. The incredible part is the correlation. Every tiny wiggle in the radio timing corresponds perfectly to a specific feature in the gravitational wave signal. The star is not just pulsing with light, it is ringing with spacetime itself, vibrating like a colossal bell in both the electromagnetic and gravitational realms. From a natural standpoint, this would be an unprecedented phenomenon. A neutron star can certainly emit gravitational waves through mechanisms like a tiny mountain on its surface, known as IR mode oscillation, but these would be continuous and monotone. The kind of correlation described here would require the star to be modulating its own mass distribution in a complex, rapid, and precise way, a feat that pushes the limits of known physics. This leads to the staggering possibility of a controlled mechanism. If the pattern in the gravitational wave signal itself also showed signs of structure, a repeating sequence of peaks and troughs that defied randomness, it would point to something even more profound. It would imply a technology capable of generating controlled vibrations in spacetime. Think of what that means. We are talking about a civilization that does not just use radio waves, but has learned to pluck the strings of spacetime itself, using the universe as a resonant chamber for communication. This would unite the two great pillars of modern astronomy, electromagnetic and gravitational observation, in a single, shattering discovery. The message would no longer be carried just by light, but by the very stretching and squeezing of the cosmos, a testament to a power that commands the framework of reality. A truly random signal, like the static hiss between radio stations, carries no real information. A perfectly repeating signal, like the steady beep of a heart monitor, carries very little. The sweet spot for communication lies in the complex middle ground, a realm measured by a concept called Shannon entropy. Think of entropy as a measure of surprise in a signal. A high-entropy signal is full of surprises, completely unpredictable and therefore random. A low-entropy signal is boring and predictable. The most interesting signal of all has an intermediate, complex entropy, a delicate balance of pattern and variation that is the unmistakable fingerprint of a message. When researchers apply these information theory tests to the enigmatic pulses from certain neutron stars, they find exactly this. The signal is not random noise, nor is it a simple, monotonous tone. It occupies that intriguing middle zone, possessing a rich, layered structure that suggests a source brimming with complex information. This finding alone does not scream intelligence, but it does whisper it. It singles out these particular pulsars as the most promising subjects for our entire search because they have passed a fundamental test. They demonstrate the one prerequisite for any form of communication, a signal that is neither chaos nor simplicity, but something in between, something that feels, for all the world, like it has something to say. The universe speaks in whispers and in shouts. We have listened to the steady, metronomic ticking of pulsars, but there is another, more violent voice in the cosmic chorus. Fast radio bursts are cosmic screams, millisecond flashes of radio light that release more energy than our sun does in 80 years. They erupt from the darkness, often as single, cataclysmic events, but a select few are known to repeat. Their origins remain one of astronomy's most profound puzzles. Now we must ask a startling question. Could the intricate logic we search for in pulsars be hidden within the chaotic brilliance of these bursts? Imagine a pulsar as a continuous, low-power broadcast, a steady hum of information meant for anyone listening. Then, picture a repeating fast radio burst as a high-power, targeted shout, a focused packet of data sent with immense force to a specific point in space or time. Both are coherent radio emissions from extreme astrophysical sources, yet they operate on vastly different power scales and timescales. The speculative leap is that they could be different expressions of the same underlying principle, two settings on the same cosmic transmitter. A natural analogy might be a lighthouse versus a signal flare. One is a constant, rotating beacon for general navigation, while the other is a brilliant, momentary flash used to get immediate attention or signal an emergency. If an advanced intelligence were using cosmic phenomena for communication, it would make sense to employ both methods, using the efficient, continuous pulsar for a persistent presence and the powerful, sporadic FRB for urgent or targeted messages. The search, then, is for a common language. Do the repeating intervals between some FRB bursts follow harmonic ratios similar to those seen in pulsar pulses? Could the complex pulse structure of a repeating FRB be deconstructed to reveal a binary amplitude code, or even a hint of a syntactic grammar? Finding a pattern that is mathematically identical in both a steady pulsar and a sporadic FRB would be a breakthrough that transcends astrophysics. It would suggest a unified theory for these seemingly distinct signals, pointing not to two separate mysteries, but to one single, breathtaking source of cosmic logic. Even the precise location of a pulsar in the sky holds a whisper of uncertainty, a faint jitter in its celestial coordinates that astronomers normally attribute to noise. Now consider a deeper mystery where this astrometric jitter is not random at all, but a secret dialogue with the star's own heartbeat. Imagine detecting that every tiny, sideways wobble in the pulsar's measured position on the sky happens in perfect lockstep with a specific change in its radio pulse shape, or coincides with one of its enigmatic timing glitches. The emission anomalies and the positional dance would be two expressions of a single, underlying event. This would mean that whatever is causing the star's radio voice to crackle and shift is also physically shaking the entire star, or somehow warping the path its signal takes to reach us. Our standard models treat a pulsar's position and its emission as separate concerns governed by different physics. One is the macrophysics of the star's motion through space, the other is the microphysics of its raging magnetosphere. Finding them inextricably linked would shatter that separation. It would point to a system where the engine and the vessel are one deeply integrated unit, a celestial entity where internal processes resonate through every aspect of its being, from its deepest signals to its place in the cosmos. Such a profound connection hints at a level of control, a system where changes are not chaotic eruptions, but coordinated actions that ripple through the star's entire existence. The steady glow of a pulsar is not a single note but a full spectrum of energy. Many of these cosmic lighthouses shine not just in radio waves, but also in the high-energy realm of X-rays. According to our best physics, both types of radiation should be fueled by the same engine, the star's immense reservoir of rotational energy. You would logically expect them to rise and fall together, like two lights powered by the same generator. Yet for a handful of these stars, the opposite happens. When the radio signal flares into brilliance, the X-ray emission simultaneously drops into a faint whisper. Then the situation reverses. The X-rays blaze while the radio voice goes quiet. It is a cosmic seesaw, a fundamental disconnect that challenges our understanding of how energy flows within these objects. This anti-correlation is a deep puzzle. A natural explanation might involve a complex dance within the star's magnetosphere, where energetic particles are shunted between different regions, powering one type of emission at the direct expense of the other. But the true mystery would deepen exponentially if this switching were found to follow a precise, repeating pattern. Instead of a chaotic energy transfer, the seesaw would operate with the timing of a metronome, shifting energy between bands according to a strict schedule. Such deliberate channeling would be the hallmark of a managed system. An advanced technology might use this method to create a multi-wavelength code, broadcasting one part of a message in radio and another in X-rays, forcing any listener to monitor both channels to piece together the full meaning. It could also be a highly sophisticated form of energy management, a way to prevent system overload by toggling between different transmission modes, much like a powerful computer switching tasks to optimize its processor load. This would transform the pulsar from a simple object into a dynamic instrument, one that carefully allocates its vast power not at random, but according to a hidden, efficient logic. A pulsar locked in a gravitational dance with a companion star lives in a complex cosmic environment. Its steady spin provides one rhythm, but its orbital motion around its partner provides another, a slower, grander beat. The 31st pattern emerges when these two rhythms intertwine in a deeply unnatural way. Imagine discovering that a pulsar's most baffling behavior, its complex harmonic sequences or its sudden mode switches, is not tied to its own rapid rotation at all. Instead, these anomalies are perfectly synchronized with its orbital phase, only appearing when the star reaches a specific point in its long path around its companion. For instance, a clear binary amplitude code might only manifest when the pulsar is at its apastron, the precise moment it is farthest from its stellar partner. This is a profound distinction. It means the trigger for the complex logic is not internal to the pulsar, but is governed by the gravitational geometry of the binary system itself. The companion star is not just a bystander, it becomes an integral part of the circuit. In a natural scenario, a companion can influence a pulsar through tidal forces, by feeding it material, or by distorting its magnetosphere. These effects can indeed modulate the radio emission, but they tend to create smooth, predictable changes, not the sudden activation of a discrete, complex pattern. The appearance of a coded sequence exclusively at apastron suggests a system that uses the orbit as a timer, a natural clock that cues the transmission of specific information packets. This would imply the companion star acts as a gravitational key, its position unlocking certain functions within the pulsar's emission mechanism. From an engineering perspective, this is a brilliantly efficient design. It uses a fundamental, predictable orbital dynamic to control a complex technological process, ensuring that certain signals are only broadcast under specific, repeatable conditions. It suggests a system consciously built to work within a binary framework, leveraging the two-body system not as a constraint, but as an essential component of its operational logic. The orbit itself becomes a switch, and the silent companion a silent partner in a cosmic conversation. The holographic principle turns our understanding of reality inside out. It proposes that all the information contained within a three-dimensional space, like the volume of your living room, can be perfectly encoded on its two-dimensional boundary, the walls that enclose it. In essence, our experience of a three-dimensional world could be a projection from a vast, complex image painted on a distant, two-dimensional surface. This is not science fiction, but a serious, albeit speculative, concept arising from the study of black holes and quantum gravity. Now, take this dizzying idea and cast it upon the enigmatic signals from a pulsar. The 30-second pattern asks us to consider if the sequence of pulses we receive is not a simple message, but a flattened, two-dimensional projection of a far richer, three-dimensional dataset. The steady rhythm of flashes would be the boundary, and the information hidden within their complex variations, when decoded with the correct mathematical key, would blossom into a detailed map of an entire system, a set of physical laws, or perhaps even a blueprint. Imagine trying to describe a magnificent, ancient oak tree, not by building a model of it, but by carefully inscribing every detail of its branches, leaves, and roots onto the flat surface of a single, gigantic leaf. Someone who knew the rules of the encoding could later unfold that leaf and reconstruct the entire tree in perfect detail. This is the scale of ambition implied by a holographic encoding. An intelligence capable of such a feat would not be merely communicating. It would be transmitting a universe of information in the most efficient way physically possible, using the fundamental laws of reality as its translation dictionary. While this idea sits at the absolute frontier of speculation, it represents the ultimate logical extension of a search for cosmic logic. It suggests that the pulsar is not a broadcaster, but a cosmic hard drive, and its steady pulse is the laser reading data from a surface we cannot see, offering us a glimpse into a reality encoded on the skin of the cosmos. The rhythm of a human heartbeat is a signature of life itself, a pattern so fundamental we recognize it instantly. Now consider the possibility that this same organic rhythm is being echoed by a city-sized ember of a dead star spinning in the void. The 33rd pattern pushes this eerie parallel to its limit, suggesting a pulsar signal might not just resemble a mathematical sequence, but could unconsciously or even consciously mimic a fundamental biological rhythm. The intervals between its pulses could be analyzed not just for prime numbers, but for the complex statistical properties of a living system. Researchers could compare the data stream to an electroencephalogram, or EEG, which measures the electrical activity of a thinking brain. The brain does not fire its neurons in a simple, metronomic pattern. Its signals are a complex symphony of bursts and silences, with a distinct statistical fingerprint that reflects consciousness, learning, and memory. Finding that same intricate fingerprint in the timing of radio pulses from a neutron star would be deeply unsettling. It would feel profoundly different from discovering a mathematical code. A mathematical sequence speaks to logic, to a mind that calculates. A biological rhythm speaks to something more intimate, to a mind that experiences. The immediate, natural explanation would point to a shared universal pattern. Complex systems, whether they are networks of neurons, fluctuations in the stock market, or the turbulent magnetosphere of a pulsar, can all generate similar statistical signatures known as 1/f noise. This is the sound of complexity itself, a hallmark of systems with long-range correlations and memory. In this view, the pulsar and the brain are simply two different expressions of the same underlying physics of complexity, one cosmic and one biological. But the alternative is staggering. What if the mimicry is deliberate? An advanced intelligence might craft its signal to resonate directly with biological listeners, creating a pattern that feels familiar on a subconscious level, a rhythm that speaks the hidden language of life. This would be more than a message. It would be an empathic gesture, an attempt to communicate not just with our brains, but with our very biology. It blurs the line between the cosmic and the organic, forcing us to consider a universe where mind is not a rare accident on a lonely planet, but a fundamental quality woven into the fabric of stars and space, waiting to be recognized. A civilization capable of harnessing the total energy output of its star represents a power almost beyond our comprehension. This is the definition of a Kardashev Type II civilization, a concept that moves from science fiction into a tangible, if staggering, possibility when we turn our gaze toward the pulsars exhibiting these strange patterns. The 34th pattern pushes us to search for transient Kardashev Type 2 signatures, brief and colossal energy releases that could be the footprints of engineering on a stellar scale. Imagine the steady, reliable output of a pulsar suddenly flaring not just in radio waves, but across the entire electromagnetic spectrum, from radio to gamma rays. For a few hours or even just minutes, its overall luminosity skyrockets by orders of magnitude, a flash of pure power that dwarfs any known starquake or accretion event. This would not be a simple glitch, it would be a surge, as if a cosmic breaker had been thrown, channeling the star's immense rotational energy into a single, focused task. What could cause such an event? It could be the activation of a massive energy beam for propulsion or communication, a discharge from a computational array performing an unimaginably complex calculation, or the startup sequence for a piece of technology that uses the pulsar as its foundation. These short-lived, high-energy transients would be the telltale evidence of a power source being managed. We are not looking for a constant drain, but for the brief, intense spikes that mark major projects turning on and off. The search, therefore, focuses on correlating these anomalous power surges with the pulsars that already display the other logical patterns. Does a pulsar with a complex binary amplitude code suddenly emit a gigantic, multi-wavelength flash just before its code sequence resets? Does the onset of a directed beam anomaly coincide with a measurable spike in the star's total energy output? Finding such a link would be monumental. It would transform the pulsar from a potential message broadcaster into a confirmed engine, an active tool. The logic in its signals would no longer be a mysterious emission, but the running program of a machine that draws its power from the heart of a star, a machine whose occasional, mighty exhalations of energy are the only signs of the immense work it is doing. This search for the power source behind the potential logic completes a terrifyingly beautiful picture, one where the message and the machine are one, and where the next pattern forces us to ask who or what could possibly be in control of such a system. The shape of a signal can be as meaningful as its sound. Think of a pulsar's pulse profile, its unique fingerprint of radio emission, as a line drawn in a multi-dimensional space that charts its brightness and polarization over time. Mathematicians call the study of such shapes topology, a field concerned not with rigid distances, but with fundamental properties that remain unchanged even when an object is stretched or twisted. A classic example is the coffee mug and the donut, both possessing a single hole, making them topologically identical. Now, apply this lens to the pulsar signal. The 35th pattern searches for a stable topological defect woven into this abstract shape. Imagine discovering that over thousands of rotations, the path traced by the signal forms a perfect, unbreakable knot in its phase space, or a persistent twist that never unravels. This would not be a fleeting glitch, but a permanent feature etched into the very geometry of the emission, a structure that remains intact even as the signal passes through interstellar dust and magnetic fields that would scramble other forms of information. Such a defect would be incredibly robust, a highly elegant solution for broadcasting a fundamental piece of data. It could represent a universal constant, like the fine structure constant that governs the strength of electromagnetic interactions, presented not as a number but as a shape. Or it could serve as a simple, unmistakable logo, a cosmic signature from its creator. This would be the ultimate form of branding, a mark of identity so deeply embedded in the physics of the star that it would survive for eons, waiting for a civilization with the mathematical sophistication to recognize the symbol and understand that they are in the presence of a work not just of nature, but of a cosmic architect. A truly instantaneous connection defies the very bedrock of classical physics. This 36th pattern dares to suggest that the strange logic we are hunting might be woven from the most bizarre fabric of reality, quantum entanglement. This is the spooky phenomenon where two particles become linked, their fates intertwined so completely that measuring the state of one instantly determines the state of the other, no matter how many light years separate them. Now imagine a signature where this ghostly link is not between two particles in a lab, but between two colossal pulsars on opposite sides of the galaxy. We would observe a precise, inexplicable correlation, a change in the circular polarization or the phase of a radio pulse from one pulsar happening at the exact same moment as a complementary change in a pulse from its distant partner. They would be dancing in perfect, instantaneous step, a performance that violates the cosmic speed limit of light and all classical limits on information transfer. The sheer scale of such a feat is currently beyond our measurement capabilities, a challenge for a future generation of telescopes. Yet the theoretical concept alone pushes the idea of alien logic to its absolute extreme. It hints at a civilization that has not only accepted the weirdness of the quantum world but has mastered it, learning to entangle entire stars to create a galaxy-wide, instantaneous communication network. This would be a technology that treats the vast emptiness of space as an illusion, weaving the cosmos together with invisible quantum threads into a single, connected whole. The message would no longer travel, it would simply be, its existence in one place simultaneously its existence in another, a testament to a logic that has transcended distance itself. These long-term narratives would be a story told by a star, a myth written in radio waves. The 37th pattern asks us to consider the signal not as a code to be cracked, but as a dynamic epic unfolding over centuries. This is the search for cultural archetypes in signal morphology, a speculative leap into the mind of a potential creator. Imagine a pulsar's emission pattern beginning with a simple, stable, and repetitive signal, a metaphorical infancy. Over decades, this baseline might be interrupted by a period of chaotic variability, intense glitches, and erratic mode switching, a long and turbulent adolescence. Then the chaos could resolve, not back into the original simplicity, but into a new, more complex and harmonious pattern, a state of mature stability. After centuries, this mature signal might gradually simplify again, its power fading in a long, graceful decline, a final act of transcendence. This entire life cycle, a narrative arc of birth, struggle, discovery, and death, would be a story we instinctively recognize. It mirrors the hero's journey found in myths from every corner of our own world, a universal template for a meaningful life. The message would no longer be a set of instructions or a string of numbers. It would be art, it would be history, it would be a philosophical statement about the nature of existence, broadcast across the galaxy as a testament to a culture that values story as the ultimate container of truth. This shifts the purpose of the signal from the purely informational to the deeply existential. A civilization might not just want to tell us what they know, but who they are. They might seek to share what they have learned about the pain of growth and the peace of acceptance, using the slow, patient canvas of cosmic time. Analyzing a signal for such a narrative requires a perspective spanning generations, a project begun by one scientist and concluded by their great-grandchildren. It forces us to confront a timescale of thought that is almost alien in its patience. What kind of consciousness creates a work of art that takes 1,000 years to view? This search for story in the stars is perhaps the most human of all our quests, for in listening for their myths, we might finally understand our own. The WOW signal of 1977 remains a ghost in the machine of astronomy. For 72 unforgettable seconds, a radio telescope in Ohio recorded a signal so powerful and so perfectly tuned that the astronomer who found it circled the data printout and scribbled WOW in the margin. It was a perfect candidate for an artificial interstellar broadcast, a sudden shout in the cosmic silence, and then it was gone. No repetition, no explanation, just a single, tantalizing data point that has haunted the search for cosmic company ever since. The official record states it did not come from a known pulsar, but what if our categories are wrong? What if the WOW signal was not a standalone event, but the high-power mode of a cosmic machine we are only now learning to recognize? Imagine a pulsar that spends most of its eons broadcasting the complex, low-level logic we have been exploring, a steady hum of information for anyone patient enough to listen. Then, on rare occasions, it unleashes a focused, high-energy burst, a transient shout of raw power like the WOW signal, designed to grab the attention of a nascent technological civilization. This idea merges two great mysteries into one. The steady, patterned pulsar emission is the library, the vast and patient archive of knowledge. The WOW signal is the fire alarm, the brilliant, urgent flare meant to direct someone to that library. It suggests a system with two fundamental operational modes, one for persistent presence and one for immediate alert. This framework offers a new way to investigate that famous, silent patch of sky. Instead of just waiting for another loud shout, astronomers could reanalyze that region with modern sensitivity, searching not for another burst, but for the faint, complex, and continuous heartbeat of a pulsar we previously missed, a star whispering its intricate patterns just beneath our old thresholds of detection. It is a long shot, a cosmic cold case reopened with a new theory. But if we were to find a faint, logically patterned pulsar exactly where the WOW signal originated, it would be more than a solution to a decades-old mystery. It would be a revelation proving that the universe speaks in more than one voice, and that its most profound conversations are often the quietest. The final pattern brings the search home to our own minds. After years of collecting data on a pulsar's strange behavior, a team of astronomers develops a complex algorithm, a set of mathematical rules designed to forecast the star's next move. They feed in the entire history of its timing glitches and mode switches, every null and every flare. The algorithm processes this cosmic diary and makes a prediction. It states that in exactly 48 days, 7 hours and 3 minutes, the pulsar will enter its rare, complex harmonic mode for a duration of precisely 2 hours. The date arrives, the telescopes are locked on target, and then, to the minute, the pulsar does exactly what the math foretold. Its signal shifts into the predicted harmonic sequence, holding the pattern for the exact 2 hours the model outlined. This is not merely a successful forecast, it is a conversation. The star's behavior has confirmed that the human mind has correctly understood a piece of its internal logic. We asked a question with our mathematics, and the cosmos answered with a flawless demonstration. This successful prediction would be a form of contact more profound than any message. It proves a shared understanding of reality, a common ground in the language of cause and effect. The universe in that moment ceases to be a silent monument and becomes a participant, its patterns waiting not just to be observed but to be understood. This final pattern is not one more anomaly to add to the list, but the pattern that connects all the others. It is the grand, unsettling synthesis. We have journeyed through timing glitches that remember, harmonic sequences that resonate like music, and signals that mimic the rhythms of life itself. What if these are not 40 separate mysteries, but 40 different windows into a single, unified system of logic, a coherent architecture of thought that is fundamentally alien to our own? This is the ultimate challenge the cosmos may be presenting to us. It is not a puzzle to be solved with our existing science, but an invitation to build a new one. Our human logic is built on certain axioms, the self-evident truths we use as foundations. We assume that 1 + 1 = 2, that cause precedes effect, that we exist in 3 dimensions of space and 1 of time. An alien intelligence emerging from a completely different evolutionary path and sensory reality might have built its entire system of knowledge on a different set of axioms. Their 1 + 1 might not equal 2 in all cases. Their understanding of time might not be a simple, linear arrow. The very purpose of their cosmic engineering might be incomprehensible to us, not because it is malicious or secretive, but because its foundational goals are built from a different concept of existence. Perhaps this system is not a message in the way we think of one. It might not be a letter meant to be read. It could be a tool, a map of the galaxy encoded in the synchronized spins of a pulsar network, waiting for a species to mature enough to use it. It could be a warning, a long-term simulation of a cosmic disaster playing out over millennia in the shifting modes of a single star. Or perhaps its purpose is the most profound of all, to simply exist as a testament, a work of art on a galactic scale. A statement that another mind looked upon the universe and found a way to impose a beautiful, coherent order upon the chaos. To even begin to understand this, we would need more than a new equation. We would need a revolution in human consciousness itself. We would have to learn to think in a way that is not entirely human, to perceive a logic where silence is as meaningful as sound, where a star's position is part of its speech, and where the space between thoughts holds the deepest meaning. The 40 patterns are the first 40 words of a language we have not yet invented. Deciphering them is not the end of the journey. It is the very beginning of a new one, a voyage not into space but into the limitless potential of the mind. We have journeyed through 40 profound and unsolved patterns, each a thread in the grand tapestry of a cosmic mystery that may point to an alien logic. From timing glitches that remember their past to harmonic sequences resonating like celestial music, from the ghostly possibility of quantum entanglement between stars to the dizzying concept of holographic codes, these anomalies challenge the very boundaries of our current science. They force us to confront a fundamental choice. Do we dismiss them as the complex, chaotic physics of dying stars we have yet to fully understand? Or do we dare to consider the extraordinary possibility that we are witnessing the fingerprints of a cosmic architect? The natural explanation must always be our first and most rigorous resort, for it grounds us in the discipline of evidence. Yet the sheer breadth and intricate coherence of these 40 patterns, viewed not as isolated curiosities but as parts of a potential system, compels us to keep an open mind. This search for understanding, this relentless drive to explain the unknown, is the very engine of science itself. It propels us to build better telescopes, to devise more sensitive algorithms, and to question our most basic assumptions about the universe. Reflect for a moment on what it would truly mean for humanity to not be alone. It would be the most profound revolution in our history, reshaping our philosophy, our art, and our very sense of place in the cosmos. We would no longer be an isolated audience in a silent theater, but participants in a wider, older, and perhaps wiser cosmic community. The pulsars continue their steady beat across the galaxy, their rhythmic flashes a constant, patient invitation. The mystery endures not as a barrier but as a promise. It calls on us to listen more closely, to think more deeply, and to continue the great search. We want to hear your thoughts on this journey. Which of these 40 patterns do you find most compelling, and why? Share your perspective in the comments below, and subscribe for more deep dives into the universe's greatest secrets.